Hello, good evening, everybody. We are excited to kick you off. Thank you for waiting with us. We are going to get started in just a little bit. So everyone sit tight and we're going to have a wonderful, fun night. Normally, if this were in person, we would say, who is hiring? Unfortunately, there's only 3 people on screen right now, so you can't just stand up in your seat and say, hey, I'm hiring. So if you would like to hire somebody, go to the NYHackR Slack and go to the job postings channel and post your job. Likewise, if you want to get hired, go to the job postings channel and find a job. Hopefully soon we'll be back and we can actually find jobs in person. But anyways, go to the job posting. It's a really great way to get hired or to hire someone. Since I am on camera, I am hiring as always. We always have a lot of positions available. We are growing, looking for Linux admins. We are looking for sales, looking for Shiny devs, looking for data scientists. So if you want a job with me at my company, Lander Analytics, go to landeranalytics.com/careers. We have a whole bunch of roles up there. We're fun to work with. In R news, hope everyone saw that R 4.2 came out recently. I'm very excited because the native base pipe now works with an underscore placeholder in case you want to pipe the argument to a different spot. So I am very, very excited about that. In our normal tradition, which I know we can't all be together, I got my pizza today from Rocco's. You can see it was cooked in a pan. You can tell by the gaps and the browning. Good cheese lock, because these grandma slices often have cheese lock. This isn't Sicilian, it's a grandma slice. Those of you in the New York, Long Island area are probably familiar with grandma slices. Those of you outside, maybe not as familiar. It's like a Sicilian, but the dough doesn't rise first. It's so that they cook it before the dough can rise. So it's a nice dense crust. So those of you who are eating or drinking or whatever, hop in the chat. Let us know where you got your pizza from, or your dumplings, or your pretzels, or your flatbread of pepperoni and pineapple. Oh, it's a flatbread. It's not pizza, so we'll let that one go, Jeff H. If anyone else has good pizza or good food or anywhere, let's share where you're eating from. Because those of you who used to come to the in-person meetup know how important pizza was to our events. And so I'm keeping the flame alive by going to places like Rocco's every month in different places. So hope everyone else is too. We got Pav Bhaji. That's like an Indian sloppy Joe and from Chicago. Cool. Yeah, let us know where you are, folks, too. Let us know your food and let us know where you're coming in from. That's always fun to see people. Jeff H, as close as you can get. We got squash soup. All right, cool. So I hope everyone's enjoying your food. And let us know in the chat. I love seeing this. Josiah, do you have pizza from somewhere? Did you get pizza?
No, I didn't. I haven't eaten much yet.
Oh, we need to get you some food. We'll deal with that after you're talking to us about GSP. We have someone from Orlando who's not having pizza, much like Josiah. We'll talk later, Josiah. We'll fix that. We have a new website. I know I talked about it last month, but if you folks go to nyhackr.org, it has been dramatically redesigned thanks to Joe Marlowe and Nicole Del Judas. They have done an amazing job designing our new meetup website in R using R Markdown. Highly recommend checking it out. You can see our pizza poll, which is actually in the process of that's being completely revamped. You can see all the we've had 13 years. Actually, this month is the 13th anniversary. Oh my goodness. This is the 13th anniversary of the meetup. It's been going on for 13 years. I'm really excited about this. Yeah. So you want to see slideshows from the past 13 years and videos in the past 8 years, roughly, go to nyhackr.org and check out all this beautiful website that Joe Marlowe and Nicole Del Judas put together. We are very, very excited about that. It's a very good website, much better than the previous one, which I had built the previous one and it just wasn't as amazing as it is now. It was bad. Let's be honest, it was bad. Now it's amazing. So we're very happy about that. We want to thank EcoHealth Alliance for setting us up with a Zoom link. They've been doing that for over 2 years now. Actually, no, it's exactly 2 years. It started, April 2020 is when we had our first virtual meetup. So not only is this the 13th anniversary of the meetup, but it's the 2nd anniversary of us being virtual. So take that for what it is. But we are pretty excited. We have a few things happening. Next month, May, will be another virtual meetup. All right, it'll be a 100% virtual meetup in May. We have a speaker ready to be announced soon. We'll announce in the next few days. So May will be virtual. But then June, we just 95%, was always in a confidence interval, secured venue space in Midtown Manhattan for our first in-person and virtual meetup in 2 years. It's going to be a hybrid, folks. We're going to be in person. Those of you in New York City will be there in person. Those of you not in New York City, we are going to have it live streamed on YouTube. All right. We are very, very excited about this. We are not quite ready to announce the details yet. It will be the first week in June. In fact, it'll be June 1st or 2nd. We are very excited about this. Not going to have venue details yet. I don't want to jinx anything. Once we get everything locked down, I am so very excited to have this in person and virtual. So if anyone wants to come in from, I see people from Saudi Arabia, from Vermont, from London, from South London, from Brazil, Miami, South England, sorry, not South London, from Austin, from all over the place, Buenos Aires, Orlando. So folks, Chicago, I saw. You'll also be able to join us in June when we're in person and virtual. We're going to try to make it like an equal event, right? The virtual and in person will be just as good. That said, we have this space, but we can't rely on one spot to have space every month. So if you have an office space that can hold about 100 people in your cafeteria, in your break room, at your desk, wherever, anywhere in Manhattan, I was about to say all of New York City. I don't mind, having events all over the city, but to make it most accessible to people coming from the tri-state area, Manhattan is kind of important. So if you have space anywhere in Manhattan, let us know. We need to have a whole bunch of hosts. In the past, we had 4 regular spaces we would go between. If you have office space, let us know, because we're excited for June, but we want to make sure July, August, September is available to us. We have another in-person event coming in June. It is our 8th annual, it's 8 years now, New York R Conference. We are really, really excited about the New York R Conference. It's been virtual the past 2 years. This year, it will be both in-person and virtual. It'll be in person in Midtown East at the French Institute, and it'll be virtual on Hopin, the platform that's really great that we've used the past 2 years. There'll be workshops on June 8th, and that will be Max Kuhn teaching machine learning, Dean Natali teaching Shiny, Jeroen Janssens teaching Python for our users, and Malcolm Barrett and Lucy D'Agostino McGowan talking about causal inference. Malcolm, the causal inference workshop will be only virtual. Max Kuhn and Jeroen Janssens will be both in person and virtual, and Dean Natali will just be in person. Then the actual conference itself takes place June 9th through 10th. We have an amazing lineup of speakers. We have Andrew Gelman, Asma Toomey, we have Max Kuhn, we have Wes McKinney, Sarah Catanzaro, and then we have a special live recording of a podcast. John Crone, who actually did a recording last year, will be doing another recording, and his guest this time will be Hillary Mason. So we're very excited for this live podcast of John Crone and Hillary Mason. It's going to be a really fun time. And of course, if your company is looking to sponsor either for hiring or to sell your services, let us know. Again, it'll be both in person and virtual. And lastly, if you're a member of this meetup, you get a discount. Use code NYHackR for a 20% discount. Go to rstats.ai and use the code NYHackR for a 20% discount. Since you're here tonight, you could use code NYHackR30 for a 30% discount to the conference. So I hope you can come. All right. With all that, questions, go to Slack. We're going to give away a free ticket to the New York R Conference. We're going to be in person soon. You can check out our new website. Lots of cool stuff. So I am very excited to announce this next speaker. I first met him at a conference. I was giving a workshop, and he was one of the attendees. And I immediately, we talked to each other, had a fun time chatting. I've seen him at a bunch of my workshops. I think we've seen each other in person other places. And I am very excited, not just selfishly, because I enjoy spatial analytics, because I think everyone's really going to enjoy this talk. Everyone, please give a virtual welcome, applause to Josiah as we bring him onto the virtual stage. Thank you, Josiah. Welcome.
Thanks, Jared. Hey, everyone. My name is Josiah Parry. I'm super excited to be with y'all tonight to discuss exploratory spatial data analysis in R. I do feel obliged to tell you a little bit about myself, and I promise to keep it rather short. I'm not really fond of watching recorded videos and fast forwarding 10 minutes, and then it's still a biography. So I work at a market research firm called the NPD Group, which is headquartered in New York, but I'm actually in Virginia right now. My background is in the social sciences. In 2020, right as the pandemic started, I graduated from Northeastern University with a master's degree in urban informatics. Prior to that, I studied sociology and anthropology at a small state school in New Hampshire. And then during that time, I realized I was actually really interested in statistics and geographic information systems. So I left with some minors there. But I wouldn't call myself a math expert. I got a D in Calc 2. I pretty much struggled with trig sub. But it was around 2016 when I really started to take R seriously. So my goal for today is to introduce the fundamentals of spatial data, the first law of geography, the objective of exploratory spatial data analysis, or ESDA, and then the fundamentals or the introduction to the SFDEP package, which I just got on Crayon a week or so ago. So before we start talking about exploratory spatial data analysis, I think it's really important that we review exploratory data analysis. And I really like this quote from the National Institute of Standards and Technology, or NIST. They define EDA as follows. Exploratory data analysis is an approach/philosophy for data analysis that employs a variety of techniques, mostly graphical, to maximize insight into a data set, uncover underlying structure, extract important variables, detect outliers and anomalies. Another really great quote from R for Data Science by Hadley Wickham says, EDA is not a formal process with a strict set of rules. More than anything, EDA is a state of mind. So in essence, the objective of EDA is to discover potentially explicable patterns. It's an art and not a science. To me, it's all about getting a tactile feel of our data, maybe develop an intuition for where things may or may not belong, what patterns that may exist in the data that you may not have discovered, or what could be discovered further. And as said in the NIST quote, EDA heavily relies on data visualization to interrogate data, and it also makes use of descriptive statistics for identifying outliers or any sort of other thing there. Pictures are worth 1,000 words, graphs and charts probably 10,000. So I do want to talk about exploratory spatial data analysis, but before we do that, I think it's really important that we talk about spatial data. And there are so many types of spatial data, and you're familiar with some, even if you don't think you know spatial data analysis. It comes from tons and tons of different sources and domains, such as transportation, ecology, environmental sciences, demography, and probably a ton more. So just to explore a few. Here we have some charts on the right of street networks in 4 cities: New York, Paris, Tunis, and Atlanta. Street networks are probably one of the most common and familiar types of spatial data that we might be exposed to. From these spatial networks here, this road networks, we can learn a lot about maybe how old urban areas are, like if we look at Tunis, what type of transportation is emphasized, where parks may be, and this type of data can be used for transportation planning and routing. So think of things like Google Maps. On this graphic here, we can see the distribution of flowers in Pune, India, and how the color of those flowers change by month. This is actually a really cool GIF that was created by my friend and former classmate at Northeastern, Asim Deodar. And ecologists have been using spatial data to track locations of plant species throughout landscapes, evaluate how habitat for these species looks. You can think about this from the biological perspective, where species are, so on and so forth. Another one, which I find super cool, is satellite imagery. So these are big cameras in space, which takes pictures of the Earth. So this one we have here on the right is imagery derived from the Landsat 8 satellite. Satellite imagery is the backbone of the remote sensing domain. And satellites can capture all sorts of color ranges that we can't see with our own eyes. So we can use those light combinations to show different things in landscape. For example, we can explore where water is, or urban surfaces, or vegetation, so on and so forth. And satellite imagery is becoming even more widespread and available, and it's used everywhere from weather forecasting to military intelligence, right? And this actually, in specific, this third section of this satellite imagery is what really got me interested in spatial analysis, where we can use satellite imagery to look at urban landscapes. So that's really what got me excited about spatial data. And then here we have regional data. So on this choropleth map, which is a map that has associates colors to predetermined regions, it was created by the Census Bureau to show places that they deemed hard to survey populations. And choropleth maps are probably the most common type of geospatial visualization that there is. You've probably made one or seen it in the New York Times or Washington Post or wherever you might have seen one. And the choropleths use regional data. So the regional data is these enclosed shapes that we see here. And regions can be any predefined shape in space. So it could be tracts, counties, zoning areas, states, you name it. But the challenge with this type of data is that these boundaries can be rather arbitrary and can introduce, if there's any economists here, aggregation bias. Or in the geographic terminology, it's a modifiable areal unit problem where the value associated with the shape is determined based on how we draw it, right? So that's one of the downsides of these types of data, but it's what we're going to be exploring a lot today. And then also, I couldn't leave out digital elevation models. So here we can see a DEM for short that was created with Ray Shader by Tyler Morgan Wall. It is so cool what you can do in R with spatial data. I just couldn't omit it. And DEMs are really, really awesome because they can be used for natural disaster planning, identify floodplains, landslide areas, where one should put a runway for an airport, so on and so forth. And while I do find the term big data to be a little overused, I would be remiss if I didn't mention the impacts that the growth of big data has really had on spatial data. Much of the data that is touted as big is naturally spatial. So some pertinent examples might be the use of light detection and ranging, or LiDAR, point of sale data, point of interest data, Internet of Things devices and sensors, municipal services like 311, that was really, really big for me and my program at Northeastern, and road network data, so things like OpenStreetMap. LiDAR is a type of remote sensing imagery. It works by shooting lasers out and measuring the amount of time it takes for that laser to hit a surface and come back. So by measuring that amount of time, we can figure out the distance it takes, or distance between that camera in essence. And then from that, we can create entire 3D environments. So LiDAR is used in autonomous vehicles to continually evaluate like surrounding areas and identify objects and that kind of things. So with the development of drones, we're able to get a lot more LiDAR data and geospatial data. Now, POS data I think is really cool. There might be a lot of folks in the retail business here. For example, at NPD, we track sales from over 600,000 retailers. Each sale is recorded. Each sale happens at a store somewhere, and those stores are located in a physical location, right? So thus those sales data is actually spatial data. And while these are used to typically track performance and create other metrics, I think there's a lot of potential here to identify spatial attributes as well. And POI data, or point of interest data, is another really fast growing industry of data vendors. So point of interest is kind of a vague term, but in essence, it's anything that might be of interest, right? So it might be a monument, hiking trail, a public restroom, a museum. So for example, Yelp is a really great resource for restaurant point of interests. Companies like Zillow and Trulia for tracking apartments and houses that are for sale. Those are really good points of interest data. Airbnb is used widely in like econometrics research. And there's also just a number of growing vendors such as SafeGraph and Carto that sell this kind of data that's really helpful to supplement other kinds of data that you might already have. But while this data is interesting and helpful, it's a little violating because they collect this data by tracking your location through apps that you might have, right? So just turn off location services when you can. So all of this spatial data typically falls into one of two categories: vector data or raster data. So vector data is coordinate based. So I like to remember this as point lines and polygons. It's fun to say. These are all based on coordinates. Whereas rasters, like the satellite imagery we saw, is a grid of cells or a pixel where each cell has a value. So when you have like a JPEG, you have a value for red, green, and blue. The same thing here is true for raster data. Now, I'm going to be focusing exclusively on vector data here on out. And there are three types of vector data that we're going to encounter. Points. So this is a coordinate point specified by the longitude and the latitude. And sometimes there's an elevation, but that's less common. And Lines are created by connecting two or more points. So that creates a line segment. And then polygons are four or more points that create a closed shape. So there's three vertices, but you need to have a point land on where it started to enclose the shape. So that's what a polygon is. Here we can see these visual representations. So on the left-hand side, we have some points. This next section here is we have lines created from those points. And then we have polygons created from those points as well. But then when we look to the raster section to the right, we can see that the raster is more or less an approximation of those points. So depending on what you're looking at or the type of data that you might have, polygons might be a better representation of a region or a shape. So as I said, we're going to be looking strictly at vector data moving forward. And then within exploratory spatial data analysis, there are two types of analysis that we might encounter. And there are some names for these, which are point pattern and lattice. Point pattern is just kind of what it sounds like. It's the analysis of point data. So that would be like species, locations, Airbnb locations, things like that. The second one is the lattice perspective. And that's what I'm going to be focusing on from here on out. If you're interested in point pattern, reach out to me afterwards. I can find you some good resources. But a lattice is a grid. And polygons, in the lattice perspective, we think of lattice as grid data or polygon data. So many of the techniques in exploratory spatial data analysis fall into this lattice category. Here are some nice lattices. We have a nice lattice on a pie, a lattice for your garden, and then some sort of network lattice. So one more thing before we dive into exploratory spatial data analysis. The first law of geography. So in 1970, Waldo Tobler wrote this quote, which is now the most important quote in geography. He said, everything is related to everything else, but near things are more related than distant things. And that's really the premise that we're going to be after in exploratory spatial data analysis, ESDA. Things that are close to each other tend to be more related than things that are further apart, but everything's related. So ESDA extends EDA to spatial relationships. We're focusing on how values are distributed across a landscape. We're wanting to explore Tobler's first law, right? Are like values clustered together? Are things further apart? Are there values in the landscape that are dramatically different than what it's expected, right? So an ESDA typically focuses on two topics. Those are two spatial characteristics: spatial autocorrelation and spatial heterogeneity. Spatial autocorrelation is the correlation between a value and the values surrounding it, or its neighbors, or its neighborhood. Whereas spatial heterogeneity is the uneven distribution of values across the landscape. Much of ESDA is really focused on this idea of spatial autocorrelation, and that helps inform analyses that might identify what are called spatial regimes, whatnot. So EDA in general compares part to the whole. So how does one observation look in context to everything else, or in context to its subset of the data? Whereas ESDA compares a part to its neighboring parts, not necessarily the entirety. So we like to evaluate a location's value relative to the values of its neighborhood. And the neighborhood is fundamental to ESDA. But like, how do we define what a neighborhood is? What are they? Well, there's many different ways that we can accomplish or define what a neighborhood is. But when we're thinking about lattice data, there's really one main way. So to get an idea, let's just look at a chessboard. This is an accurate chessboard. It's a hobby of mine. So think of each square in this chessboard as a region or a polygon in our data set. Each one of these squares has a neighborhood, but we need to think about how do we actually define that neighborhood. So when we have lattice data, we typically define neighbors based on their contiguity. And contiguity just means to be touching or next to something. So contiguous neighbors are those regions that touch our region of interest, or our focal region. And there are two main types of contiguity that we refer to here. They're both named after the chess pieces. So rook and queen contiguity, which are based on the way that the respective pieces move in the chessboard. rooks can move vertically and horizontally. And then queens can move the same way as a rook, so vertically, horizontally, and then along both diagonals that it has. So so there's rook contiguity and there's queen contiguity. And rook contiguity is defined by what's touching on its sides. And then queen contiguity is what touches our region of interest on its sides and also its vertices. So let's look at the contiguity of the Queen's Gambit. Great Netflix show, also my favorite chess opening. So this white dot is D4, the position D4, or the coordinates 4, 4. If we take D4 as our focal point, the squares that it touches on its sides are C4, D3, D5, and E4 squares. So based on rook contiguity, we have 4 neighbors just based on their sides. Okay. Now, if we take a look at queen contiguity, every surrounding region is considered a neighbor. And this is generally the preferred type of contiguity. When we choose rook contiguity, it's typically for a theoretical reason that makes sense for your data. So in my background of urban sciences, we're actually generally interested in queen contiguity because we want to know about neighborhood effects. How does one region impact the immediately surrounding ones? So in this case, we have 4 additional neighbors, the ones that are touching by the vertices. So that's C3, C5, E3, and E5. So now we have 8 total neighbors in our neighborhood. So if we created a connectivity map of all the squares on the chessboard for rook and queen contiguity, this is how it would look like. So on the left-hand side, we can see only vertical and horizontal lines. On the right side, we have the same lines, but now we have diagonals going across. And that's kind of how we can envision contiguity. But spatial data is never really as nice as a grid unless you maybe make a grid and count the number of points in those grids, right? That's a different story. So here we can see the queen contiguity of a region in France and its neighbors. The region in interest is black and its neighbors are gray. So we can see that all surrounding points are, all surrounding regions are considered a neighborhood. So that helps us frame how we define a neighborhood. But naturally, the next question is, well, how do we evaluate what this neighborhood is? So we really do this by comparing a point value, so a region of interest, to the surrounding neighborhood point values. To compare the neighborhood, to compare the observed value to the neighborhood, we create what's called a spatial lag. The spatial lag is just the expected value or the average value for that neighborhood. But when we compare to our neighborhood, how much influence should each neighbor have in calculating that expected value, right? And that's a tough question. When we think of Tobler's first law, where nearer things are more similar to distal things, it would only be natural for the neighbors that are closer to have more influence. The influence that a region has in identifying the expected value is measured as the spatial weight. But when we think about polygons, these are just shapes, right? There's no effective way of measuring distance because what are you measuring distance from? One vertex, one point on the side, and there's an infinite number of distances you can calculate from inside of the polygon, right? So it's kind of a challenge. We're kind of given a conundrum here. So with this lattice perspective, we're using queen contiguity. We often choose what are called row standardized spatial weights, where each neighbor, if it's touching, is given an equal weight. It's defined by this formula here, but I think of it in R terms, and it's way easier to just think of this as 1 divided by the number of neighbors that we have. So if we have 4 neighbors, it would be each neighbor would have a value of 0.25. That's how much importance it has in calculating that spatial lag or that expected value. So the spatial lag, what is the average value of the neighborhood? With the spatial weights that we have, we can now calculate what this expected value for a neighborhood is. Might get a tiny bit mathy here, but it's just basic arithmetic. You should be able to either understand it immediately, or if you're like me, maybe after an hour or two, just staring at it and trying to figure it out yourself. So some of you might be familiar with time series analysis, where a lag compares a point in time with the same thing at a later point in time or after some specified amount of time. So for example, you might compare today's values to yesterday's values, and that can help you get an idea of something. The idea is kind of similar in spatial analysis, right? So rather than comparing the value to itself, we're comparing it to its neighboring values. And as stated, the spatial lag is just the average, the weighted average of the values contained in our neighborhood, right? So we multiply the spatial weights by an observed variable y for each of its neighbors. Then we add all those things up to get the lag. And then we just do this for every single observation in their respective neighbors. So for example, say we have a random variable x. The value of x at region I is 100. It has 4 neighbors. The neighbors have values of 5, 40, 100, and 35. This is represented by xj. J is typically used to identify neighbors. We can then calculate the spatial weights by dividing 1 by the number of neighbors we have. So that would be 0.25. And then we multiply those neighbor values by their spatial weights, and then we add them up. So here for those values, we get a spatial lag or expected value or weighted average of 45. So now let's go back to the chessboard. So every square here on the left-hand side is the index of, or sorry, the row value, the row index here. So we have 1 through 64, 1 on the bottom left and 64 on the top right. The left-hand side is just the board itself. And then on the right-hand side, we have the spatial lag for each square here. So on the bottom left square, A1, it has the value 1 and its neighbors are 2, 10, and 9. So if we go to the same position on the chart to the right, we have a spatial lag of 7. And we can see on the right, it might not be so clear here, but there's some smoothing that happens with the values. So whenever we take an average, there's typically some smoothing that occurs. And let's actually apply this to a real map, right? So on the left-hand side, we have the observed crime rate in 1830s France. It comes from a very famous data set called Gary. And on the right-hand side, we have the spatial lag for that. We can see that it's kind of been smoothed out across the entire region. And then we can actually use this lag to get a sense of how an observed region compares to its neighbors using some other visualization techniques. Let's create a scatter plot of the observed variable and the lagged variable. This scatter plot of the observed variable and the spatial lag is referred to as a Moran plot. It's based on the Moran's I statistic, which we'll go over in a little bit. This plot can be super helpful to show us the spatial autocorrelation of these variables, as well as some natural clustering that they might fall into. So on the x-axis, we have the original variable. On the y, we have the lagged variable, and the slope of the regression line between these two variables is actually the spatial autocorrelation, but we'll worry about that a bit more later. So here we have a very, very basic Miran plot. In addition to the scatter plot, we place intercepts on the x and y axes of the average of each respective variable. So in essence, we're kind of plotting the z-scores here. And these quadrants actually help us identify clusters in our data set. So these quadrants show how our values cluster in space. So the top right, it indicates where high observed values are surrounded by other high values. Now going down to the second quadrant or the bottom right, we have high values, which are clustered around low values in this neighborhood. And then the bottom left, we have low values, which are surrounded also by other low values. And then on the top left, we have low values, which are surrounded by high values. And the top left and bottom right quadrants are actually very interesting, right? Because they can help us identify places that we might see a lot of spatial inequality, right? So if we're looking at household income, we might show a place where there's a lot of observed inequality around some maybe very real boundaries, whether it's like a city line, a freeway, something like that. Now, if we plot a smooth line on here with the linear regression, that's the spatial autocorrelation. And so what is spatial autocorrelation? It's the tendency of like values to cluster in space. And it's always based on this assumption of spatial randomness, where the null hypothesis is that everything is just randomly distributed across space. When data is systematically located on the landscape, that is exhibiting spatial autocorrelation. So when values, like values cluster together, we'll call that positive spatial autocorrelation. And when dissimilar values cluster together, that's called negative spatial autocorrelation. And the most common measure of spatial autocorrelation is called the Moran's eye, or in this case, I'm going to call it the global Moran's eye. So just like the Pearson's R correlation coefficient, it ranges from 0 to 1, or negative 1 to 1, where negative 1 is perfect negative spatial autocorrelation, where dissimilar values are placed together. 0 is complete spatial randomness. It's completely arbitrary where these values might fall on the map. And then 1 is perfect spatial autocorrelation, where there's very strong clustering of like values together. This is a cross product between the spatial lag and the observed variable. That's mathematics beyond me. I'm sure Jared could probably explain it. It's just not for me. So if we look at this plot again, we can see that the Moran's eye value, the spatial autocorrelation here, is 0.411. So that's a moderate amount of spatial autocorrelation. But is it significant? And that brings us to the topic of inference. And inference for spatial analysis is a little bit different. Again, as I said, we always start with the null hypothesis of spatial randomness. But traditional hypothesis testing, like the t-test, uses an assumption of normality, which isn't always actually met in spatial data. So we actually use a permutation-based inference instead. So what we do is we create random permutations of our data set and create a reference distribution where we compare our observed statistic. So we'll randomly shuffle our data, calculate Moran's eye, say 99 times, and then compare that to the observed value. So the value for calculating the simulated p-value is r plus 1 divided by m plus 1. So it's really just a ratio where r is the number of times that a random Moran's eye is more extreme than the observed one. So it's really how many times is a random Moran's eye more extreme than what we expect. So as I said, this uses conditional permutation. And this is once I got conditional permutation, spatial ESDA kind of made a lot more sense to me and how we kind of understand like what is a significant cluster. So conditional permutation is basically randomly shuffling the neighbors for every observation. So say you have an observation I and it has 4 neighbors. We randomly shuffle those 4 neighbors for every single observation. But I can never be its own neighbor because that wouldn't make sense. So we do this a bunch of times. We calculate the Moran's eye for these randomized neighbors, and then we kind of find this ratio to calculate that simulated p-value. And it's really important to note that simulated p-values are dependent upon how many simulations you run, right? So I'm always cautious of p-values, but when we're using simulated p-values, be even more cautious. Luke Anslin from University of Chicago, who's kind of like the godfather of a lot of this stuff, recommends using a cutoff of like 0.01 or 0.001 as a significance cutoff, but just always be careful and cognizant of that. So here we have 3 different histograms of our reference distributions, one with 99 simulations, one with 999 simulations, and 9,999 simulations. On the right-hand side, we can see there's a vertical line, and that represents the observed Moran's eye. And the histogram is the simulated Moran's eye whenever we shuffle that data set. So this helps us get an intuition of like, is this actually an extreme Moran's eye? Do we expect this under spatial randomness? And given our distributions here, we can see that the, I guess, mean value is 0. So fully spatial randomness, completely spatially random. Okay. So that's a good background into ESDA. And now I want to introduce SFDEP, which is a tidier interface to the SFDEP package for spatial dependence. The motivation for this actually happened back in 2019, where I was taking a class with Jeff Boeing on advanced spatial analytics. The class was taught in Python using a library called PySal. As an R programmer, I was kind of miffed. I was like, I don't want to use Python. But after a while, I learned a lot. It was actually a really great library. And then my mind was completely blown by spatial regression. And in the back of my mind, I was like, I want to do this in R. There's got to be a tool for it, so on and so forth. And then 2 years later, just mid-pandemic, I don't know what caused this, but I really wanted to relearn spatial statistics. And during that time, I discovered the SFDEP package, which is used for this exploratory spatial data analysis. But in my experience, it felt a little idiosyncratic for a tidyverse person, right? That's me. And particularly, a lot of these functionality is almost tidyverse compliant, or I wouldn't say compliant, but interoperable. So one challenge was like, I wanted to create a neighbors list, but it lacked the explicit list class. So I couldn't use that in mutate, right? So I created an issue. I was shot down because it's based on compliant, but it was still very insightful and very motivational. So immediately after, I created an R package called SFweight to just kind of create my own interface to help me do this thing. I didn't like it. It had a heavy reliance on dplyr, non-standard evaluation, and I ignored a lot of the advice that was provided in that issue. So as a next step, I decided, let me just learn more about SFDEP. So I created a pull request, introduced some new functions. In the process, I learned a whole lot and decided on a new interface for this. And I became a huge fan of SFDEP. So in building this new interface, I have some principles that I was trying to inject here. So the first is that I'm always going to use SF objects when possible, right? Or actually in general, always use SF for geometry. And I'm always going to return dplyr friendly objects when possible. So that's going to be a vector, a list, or a data frame of the same length or same number of rows as our data frame event that we're using right now. So, and then also I wanted to make sure that the functionality is not dependent on dplyr. Right. And that kind of comes down to the next bullet point where we have minimal and very light dependencies. So the heaviest dependency I have in this case is going to be SFDEP, and then some nice things like the CLI for having nice fun error and warning messages. And also so I have some new functions in here that aren't available in SFDEP, but the important thing is that it should all be compliant, right? So everything is implemented using SFDEP objects like NB and listW class lists. So to the fun stuff. So how do we make neighbors? To do this, there's a function called stcontiguities, and this takes a geometry column. By default, it uses queen contiguities, and it returns a list of class NB. And here's an example of using this just directly on an SFC object or the geometry of an SF object. And this is how that NB class list prints out. If you've used SFDEP, this should look familiar. But the nice thing is this is actually pipe friendly. So I can put this inside of a mutate function call, or in this case, transmute, just to return what I have here. So I can pass in the geometry column, and then the resultant object is this NB list column, where each element is an integer vector. And those elements contain the row positions of our neighbors. So here, the first observation has neighbors in row positions 36, 37, 67, and 69. Then from our neighbors lists, we can actually create spatial weights. And this takes an NB or class object, so a neighbors list. And we use the function SFweights, and it provides row standardized weights by default. There are other spatial weights functions for points or kernel density and things like that. But each weight in this case is the same. And then each element of the resultant list is a numeric vector, which contains the weight for each indexed observation in NB. So here we have an example of finding the neighbors and then calculating the spatial weights. And here we can see the spatial weights. Okay, so the spatial lag. To calculate the spatial lag, we use the stlag function. We provide a numeric vector and the neighbors and the lists. We have some nice use cases. The Miran plot, we can identify neighborhood averages. It's useful in regression. So this is what it would look like, right? If we wanted to create that lagged variable from the previously defined variable. Here we can see the observed value and the lagged value. Okay, so we can then use these in conjunction with dplyr to classify our Moran plot. Here we have a mutate call, which uses case when to kind of partition these data along those axes. If you want to explore this more later, we'll have the slides for you. But we can see that we're defining these clusters. Here's high, 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 low, 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 high. Okay, so the basics of creating a Moran plot, we take that now classified data frame, we pass it into ggplot, where we're putting on the x-axis the observed variable, y-axis the lagged variable. We're going to color based on that cluster variable that we just created. We're going to add the points, the intercepts, and then a theme for good luck. And there we go. So again, we can use this plot to classify our neighbors, but can we dig in a bit more? Yes. So this is where local indicators of spatial association come in, or LISAs. LISAs evaluate a statistic at the neighborhood level. So things like Moran's eye, we can evaluate at the neighborhood level, the observed value. And we use what's called the local Moran. It's also the original LISA. And the local Moran evaluates the autocorrelation within each cluster. It uses the same conditional permutation, but now the statistic is at every single observation. Okay. And to do this, we use the local Moran function. This calculates Moran's eye for each point. It identifies clusters for us, and it calculates 3 different p-values that we could choose from, and it returns a data frame that we can then use tidyr to kind of clean up a little bit. So here, this is the approach. We have our SF object. It has our neighbors and our weights. And then we create a new column called Lisa. This is going to be a data frame column. And we're passing in the variable of interest, the neighbors and the weights. And then we actually unnest it to kind of remove that data frame column. The data frame columns are always a challenge for me. The second section just illustrates how to select those columns of interest. And here we can see the results. So this is the output of the local Moran. There's a ton of stuff to work with. It contains the local Moran, the expected value, the variance, the skew, the kurtosis, and then 3 different p-values. So PII is the p-value if we assumed normality. PII sim is using the permutation approach we discussed, but it's also using a rank-based calculation. The last one here, P folded sim, is the approach that's taken in PySal, which is the Python library, which is my preference here. So this kind of follows along with that equation that we just kind of walked through a little bit. And then here we have 3 different classifications for these clusters. So how we determine our clusters really depends on where we split our values. Some people don't like to use the mean because it's very easily, I guess, affected by outliers. So people might use the median. And here we can just choose which we prefer, mean, median, or what is created in PySal. So this is a replication of the PySal clusters as well. Maybe not always. So often we don't want to show the places that might be deemed insignificant. So we could use this resultant data frame, create a new column called cluster, which if it doesn't meet some threshold, we provide that as an NA value. And then we can plot our graphic, right? So this map here helps us identify clusters in France along this variable, which is the crime rate, right? So in this bottom right, we can see where low values are clustered together. Here we can see that this value has a low value of crime, but it's surrounded by other areas that have a higher crime rate. Here, the same thing here. This, where it's red, indicates that these are high places with high crime rates that are surrounded by others that also have high crime rates. And these are significantly more crime rates. Okay, cool. So now I wanted to go through a quick worked example in our studio with educational attainment rates in Boston. I'm gonna stop my share, and if there's any questions I can answer while I get our studio open, I'd be happy to do so.
We could save them for the end, so go ahead.
Okay.
Sure.
Cool. Okay. So very briefly, I just wanted to show what the typical workflow for me kind of feels like and looks like. So this repository, data is all in script here, is going to be available on GitHub. I'll have the link for you. So what we do is we load SF, SFDEP, and the tidyverse. We'll read some data that we have in a GeoJSON file for Boston. It's now read as an SF object. It's very nice. So the first thing that we'll do in like the EDA process is evaluate the distribution. So in this case, I'm interested in educational attainment rates throughout Boston. So based on this, it doesn't seem to be anything too wild, except for the fact that there might be some locations that have no recorded educational attainment for a bachelor's degree based on the census. So while this looks fine, how does this look across the landscape, or how does this look across the census tracts in Boston? So I'm going to create a choropleth map using ggplot and fill this based on this bachelor's attainment rate based on the census. So here we can see we have some darker areas, and if you've been to Boston, this is the Roxbury area and Mattapan, and then this is also East Boston up here, which is kind of funny because it's kind of north. And then here we have downtown, Back Bay, South End kind of stuff, so richer, more affluent areas. So this kind of leads to the question, is there some spatial autocorrelation in here, right? It looks like there might be. We can see a lot of dark areas surrounded by dark areas, a little bit more brighter areas. So to do that, we'll first start by creating our neighbors and our spatial weights and store this in an object called boss and b. And then there's a couple ways we can do this. I've done this in a summarized call to calculate the global Moran. We'll pull this out. It's doing our permutations for 499 samples here. And we can see that we have a autocorrelation statistic of 0.596, so 0.6. That's quite a lot. And we can see it's rather significant. So to me, that means there might be something more to explore here. So the next thing for me to explore is always going to be the Miran plot. See if there's anything that looks kind of out of the ordinary here. And we see we have some points in these two quadrants that indicate maybe some interesting outliers where places might have lower values surrounded by higher values. So to explore that a little bit more, we calculate the local Moran using local Moran inside of a mutate. We're unnesting it, and then we're just filling it with the average cluster here. But this is informative, but it's not the most informative, right? Like we're really interested in places that kind of are that seem to be that have more spatial autocorrelation than what we'd assume under spatial randomness. So we're gonna kind of filter out those from the coloring, and we're gonna do this using mutate, just kind of a standard if-else statement, and then we can create this plot. Okay, so this is what we can see here. So we have a lot of low educational attainment, kind of in the Roxbury area, in Mattapan, and then higher in Alston, where all the college kids live. But let's just kind of see, can we associate this with the neighborhoods in Boston to get a bit better idea? So what I'm doing next is I'm reading in this neighborhoods GeoJSON here, which just has the shapes of these neighborhoods and their names. And then I want to overlay that to this existing plot. So if I just print this out, it's kind of clunky. I can't really read anything. So for this case, I just wanted to make an interactive visualization of Plotly just to kind of dive around this a bit more. So if you haven't used Plotly, by the way, you can just kind of wrap any ggplot in this function ggplotly and make it interactive. So let's zoom in here and get a better sense, right? So here we can see that Back Bay is which is a very affluent area, has higher educational attainment rates than East Boston, right? And we can see that South Boston, which is largely becoming gentrified, is higher educational attainment rates. And our studio is located right around here. Here we can see Dorchester, Roxbury, Mattapan. So yeah, with that, I just kind of wanted to provide you with an introduction to how we kind of do this in our studio. And then one last thing to share, which is kind of like, what else is there other than the local Moran? Let's find the share screen here. So it can't just be the one statistic, right? No, there's tons of things to explore, right? Whether it's point patterns, defining different neighborhoods, right? We can define these based on the nearest neighbors, places that fall within a different distance band, or neighbors of neighbors. We can also try using different weights. We can try adding a decay using a kernel. We can try using inverse distance. We can also try exploring spatial networks or using network analysis tools on spatial data, because these neighbors can be turned into a network really easily. So some other measures that there are, let me move this up a little bit, some join counts for evaluating binary variables, neighbor match tests to evaluate distances in attribute space compared to physical space, and then also things like co-location. So we can see there's asymmetries between relationships. Are 7-Elevens more located next to schools than schools are located next to 7-Elevens and things like that? So with that, I'm going to leave it. And I just want to say thank you, everyone. And if there's questions, I would be happy to answer.
Thank you very much. If we could get a round of emoji applause, I'll do a golf clap. Everyone wants to send us emojis or some kind of love in the chat. I think that's an excellent talk. So thank you very much for giving us that talk. See, there's some emojis. You made someone cry, even how good it was. I think that's what that emoji means. I'm not quite sure what the single teardrop means, but I think it was good. So thank you very much for this talk. All right, first question, Josiah, have you played a GeoParquet at all?
No, I haven't, but on my to-do list is figuring out how to use GeoSpark, and that necessitates Parquet, right? Mm-hmm. So I haven't, but it's on my to-do list.
Yeah, I've learned a little bit. I'm afraid it's just like they're just taking the well-known text and converting it to well-known binary and serializing it as text, I think, but I haven't played it enough.
Yeah, I'm not the guy, unfortunately, yet. One day.
One day, same here. And I've been playing a lot of, next question, this is from me now. Do you use PostGIS, or what do you use for like a database for this stuff?
I don't actually. So I haven't had opportunity to use PostGIS. So a lot of the stuff that I've been focusing on is like just urban data. And while they call 311 big data, it's still ran very well by my M1 chip. So I haven't had a chance to do that. So if I had PostGIS database, I would like to play around a lot with that.
When you say big, how big are we talking for 311?
A few million.
Okay.
So yeah.
Very nice.
Yeah, so a lot of work. There's interesting work done by my former advisor at Northeastern about custodianship, which evaluates 311 calls and 911 calls. So it's very interesting work.
Very cool. I'd like to see that. We have a few more questions that just came in, and since they're in Zoom, I can't copy and paste. We'll do those first, then we'll get to the other questions. I don't know why I can't copy and paste from the chat. It seems like a real issue. All right, there's a question about, could you add a function to get the clusters?
Yeah, I could. The predecessor SFweight had it. I just figure a lot of the functions from SFDEP already provides the clusters, so it's not necessary in most cases, but it does make sense if we're only calculating the lag and the observed variable, and we're not relying on calculating all these statistics. And I think I made an issue for myself a couple of days ago to do that. So
maybe soon.
Yeah.
This is a comment more than a question, but use QS to serialize the SF object. Now, from what I understand, QS, it's sort of just like a similar to an RDS object, but better and faster. So that's sort of
I have not heard of it.
Well, Josiah looks it up. From what I understand, I think it's like RDS. It's not like Parquet where like I could load it in DuckDB or I could load it in Python or R or whatever. But I do think it is like a better version of RDS, which will save it much faster.
Yeah, it seems like that. It's inspired by the FST package for fast saving. I guess it's made by Facebook, it says.
Really?
Yeah. Or uses something by Facebook. I'll have to read the vignette.
Yeah, I have to look at that too. All right, because I know I've had issues when using targets trying to save massive SF objects with RDS is slow, but if we could do it faster with QS, that'd be great. There's a question about how do you deal with multiple comparisons when evaluating Lisa? Is it Bonferroni or something else?
Yeah, that's something I've seen a lot in the literature. Is like it's kind of an outstanding problem. That's why people have the more conservative p-value estimates, and they're using the conditional simulation, the conditional permutations. I haven't seen anything in the literature that says anything. They just say be more conservative so far, and that's why we use the conditional permutation.
Okay. For choropleth, but I'm going to extend this beyond choropleth. I'm going to hijack this question a little bit.
Okay.
You have a preference between GGMAP and TMAP, and I'm going to extend that to GeoMSF, Leaflet, RDEC, and MapDeck. Like, where are you?
Okay.
Packages?
I haven't played with. So okay, my whole thing is, I know ggplot. I understand the grammar graphics pretty well. I have no reason to leave ggplot. There's a GeoMSF. I can get 99% of the things that I want with that. So I use it. I've used Leaflet, but I don't like web development. So if I ever have to touch JavaScript, I'm kind of out. And a lot of people do a lot of cool things in Leaflet. You have to touch JavaScript. But if I've not been in a place where I need to make a lot of interactive maps, so I haven't done it. I have wanted to check out MapDeck. I think I was in some discourse on Twitter about that recently. It looks actually really great, but I haven't done it. TMAP looks interesting, but it gives me like Esri vibes, where it's kind of like old school kind of flat colors. But again, like I feel so comfortable with ggplot. I have no reason to leave ggplot. I can control everything I want. There's not a north arrow, but I mean, I'm always going to be orienting my stuff northwards anyways. So I don't have a need for that.
I will say I use Leaflet a lot and never touch JavaScript. So you can do it without touching JavaScript.
Okay, cool.
Yeah, I'm not saying you should go. That's not an endorsement for Leaflet necessarily, but I'm saying like, hey, you know, you don't have to worry about JavaScript. For the one time I ever used it was I wanted to build some animations, which was quickly not worth it. So have fun using it without JavaScript.
Okay. I just remember like 2017 trying to like add pop-ups or something.
I'm good. Oh, pop-ups are all built in now. It's so easy.
Okay.
Very easy nowadays. I see a +1 and a +2 for using it without JS.
Yeah.
Because there's a whole ecosystem around like Leaflet, there's Leaf M, there's Leaf GL, there's Leaf everything.
Yeah, I saw like this new package for like having offline tiling and stuff too, which seemed really cool.
Say it again?
I think I saw a new package for having offline tiling.
Oh,
I think
Miles McBain just blogged about that. It's like not necessarily offline, but it's like in your firewall. It's like your own hosted tile.
Gotcha.
Server. Yeah, and there's all sorts of work of also like I'm gonna ask this question. Have you used Flat GeoBuff at all?
Never heard of it.
I was in a conversation with a lot of the SF folks about, hey, how do I store this stuff better in a Leaflet map so I can put it in this? And they told me, hey, maybe you could use Flat GeoBuff and use that as a way of streaming in data into Leaflet as needed.
Interesting. I've never, is this like a C library or something?
I think Flat GeoBuff, it's like I'm not sure it's C, but it's definitely like some external library.
Okay.
And R can make use of it. I think newer versions of SF, of RGDAL can read from Flat GeoBuff properly. Oh, Michael Sumner. I think you're the one of the people I've talked to on Twitter about this. Yes, Flat GeoBuff's a new format. That's great. It's great for being here. David says +1 for Flat GeoBuff. So apparently, I need to learn this because I don't know it enough.
Okay. Flat GeoBuff is a new format. Okay. Well, now I feel like a Luddite at this point.
I haven't figured out how to like use that in conjunction with Leaflet. So, Michael Sumner, if you want to give a talk in July, whenever you're physically in New York, because we're going to be back to in person, I think you're giving a talk about how to use Flat GeoBuff with Leaflet. How's that sound, Michael? Does that sound good?
Sounds like a good flight.
And assume that's a yes because he said otherwise.
Do they still have a 2-week quarantine rule in New Zealand?
They probably do, but you'll be in America for some reason, I'm sure.
Yeah.
Yeah. This is the way this works, folks, by the way. If I see you in the chat and I recognize you and you do something cool, you get pulled into giving talks. So, all right. So, Michael's, I'm going to just message you, Michael, because I have a lot to talk about. I'll copy Josiah because there'll be a lot of cool stuff. I do a lot of SF recently, so this is very apropos for me.
That's awesome.
So you talked about spatial lag, right?
Yeah.
What if you have both time and spatial? How do you do like a spatiotemporal lag?
That's something I'm actually currently exploring right now. So Esri, if you're familiar with Esri, they have a tool called ArcGIS, and it's kind of like, it is the tool that everyone uses for spatial data analysis. And they have something called, they call it a space-time cube. So they basically create like a time series of observations, but then keep track of the neighbors, right? So they incorporate the time lag and the spatial lag to calculate the same statistics, but I don't understand like the nuances of it. But that's actually my next task of functionality to build is figuring out how to actually calculate those time dependent things, but also what people do. So there's bivariate measures. So there's a bivariate local Moran. What other folks will do, or is recommended by Luke Anslin, the fellow who created that measure, is have the same variable but time lagged and then spatially lagged, right? So if you have like variable x, so if it's a bivariate measure, it's x and then the time lag of x, right? And then you do stuff with the neighbors of those and calculate cross products and things like that. But that's how you can incorporate time on some things presently. So there's things like the local C, which is another measure of autocorrelation, which there's functionality here in SFDEP and SPDEP, which can take any number of inputs, numeric inputs. So you can include the time lag and the spatial lag there, which might be a good way of finding the collocation.
Okay.
Sorry, the autocorrelation.
I see Jeff H. Posted.
Yep, the space-time cube.
Yeah, there you go. Jeff H. Is that Jeff Horner or is that Jeff someone else with an H? Because I just see the H.
I think it's Jeff Hollister from the EPA. Yeah.
Someone else. Cool.
Yeah.
Before we go, yeah, it's like.
I was just gonna say at that. So this one, oh Scott, my boss at NPD mentioned something about neighbors and networks. So yeah, you could use time series enabled network analysis like dynamic Bayes nets, which is something he's teaching me about presently right now. So yeah, there's functionality to convert these neighbor lists into tidy graphs through a thing called SF networks. So there's like a little interface, and those can be turned into iGraphs. So if there's anything that you can do in an iGraph, you can do it with the spatial network anyways. So there's a lot of places I want to go next, which is time series and also network. And I haven't figured out which one I want to choose. So if you have a recommendation, let me know.
Oh, I like both. I guess network's the thing I've been dealing with mostly with lately. So I'm going to say the network part.
Okay, cool.
Yeah. Personally, selfish. Before we continue on with questions, I saw someone else. Michael Sumner said he's willing to give a talk. Michael, message me on Twitter or LinkedIn or Facebook or email me or Slack or whatever. There's many, many ways you can touch me. You go to jaredlander.com/contact, find me there, find me on Twitter, message me because I don't have your email, DM me, whatever, and we'll get this talk going. There is next a question about, let's see, hold on. There's a question that says, do you have a resource for getting a better hold of spatial statistical basics like spatial autocorrelation heterogeneity?
Yeah, so I learned a ton. So I put the link to the documentation here. So Luke Anslin, this gentleman at the University of Chicago, he's like probably the most widely cited person in this domain. He has an open source software called Geota, which is like a UI, and the Geota documentation is phenomenal. It's not really documentation for Geota, it's just documentation for these metrics and these measures. Super great resource. I linked it there. It's just geotacenter.github.io and click the documentation tab. And then Geota Center has a YouTube where Luke Anslin posts all of his online lectures for his classes. So if I'm cooking, I'll have those on in the background. I've learned a ton from those. And then honestly, once I felt comfortable like with a lot of these measures, I just started reading the papers, right? So it took me quite a while to like start piecing apart these equations, but I think there's a lot to be gained from reading the papers after you start feeling comfortable. And The nice thing about these papers, they're like no longer than 9 pages. So it's nothing too crazy, but I've found Luke Anson's stuff so informative and helpful.
Yeah, a well-written academic paper, it does wonders. Yeah, they're great to have. Continuing on to this general theme and also the questions just coming in, and then I'll go back to the ones I collated earlier. What other fun spatial regression tools is the R ecosystem missing? Like, what would you want to add in?
That's a great question. I actually think there's a rather robust ecosystem for spatial regression. So the spatial reg package is actually really nice. I think its documentation could use cleaning and clarification. So I actually think the tools for spatial regression that exist today are actually pretty great. And I think there's also another one for origin destination regression that I forget the name of. I think it's called OD, honestly, or SI actually is the new R package I've seen. Which looked really cool. But from my experience, or from what I can tell, I think there's actually a lot of really great tools for spatial regression. I think it's these other things that need a bit more help.
Along those lines, what do you use? You did mention briefly, but the package you mentioned, is that what you use for spatial regression, or are there other packages as well?
Spatial reg is what I'm using. Also, if I do spatial regression, it's typically something pretty simple where I can actually create the variables myself. So there's something called the spatial Durbin model. If I don't quote me on this, but it includes every X and the spatial lag of that X predictor. So I can just create the lagged predictor and include it in a regular linear model. So
do you need to lag Y also?
No, but there are some models where you could lag Y. It depends on the specification. There's actually quite a lot, and I haven't fully committed to memory what each one is inferring.
What about StatStat? Is that still a package?
SpatStat?
Yeah, or did I make that up?
No, it's real. It is. SpatStat is focused mostly on ecology, and I haven't seen any like the things that that I've read from like Toyota Center and other papers mentioned on the SpatStat website. But it's also another frustration of mine that open source technology documentation should be open source, and the documentation is a book, which isn't necessarily open source.
Then let's see what's next. All right. Do you have to convert your SF objects to SP objects because you're using SFDEP?
No, great question. No, the SFDEP works. It's very flexible, right? Because it does work with SP objects. It works with SF objects now too. And a lot of great changes have been made to SFDEP to like use S2, for example, in most calculations by default. So it's actually it's a super cool package now that I know the guts of it.
That was going to be another question. Do you have to worry about projections, or are you just using S2?
Just using S2. There'll be warnings. So it's so since SFDEP is using S2, if it doesn't match it, or if it's like using lat long or whatever triggers those warnings, it provides those warnings. So that's why I like to rely on SFDEP, so I don't have to build those out. SFDEP is really, really great. It's just the interface that's a little bit different, right?
Yeah, speaking of S2, something I keep dealing with lately is keep getting like invalid polygons, and I can't even do ST make valid. There's like nothing I do makes them valid. I'm like, I don't know what I'm doing here.
Yeah, there's also something really interesting I want to understand, where they actually have like interesting measures for distance for polygons, where they like compare distances for, I think, like every vertex of a neighboring polygon, or of all polygons, and creates a different measure of distance, where the typical measure of distance is just like the centroid, which is so bad. So just because like, where is the center of a shape? So I think SC does a lot of cool stuff there as well.
There is a note from Michael Sumner saying projections, but he just gave us an ellipses. So we'll need more information, Michael, about why you don't like S2, or if that's what you are saying. But like, it's got to be a talk soon. All right, that's decided. That's it, because I know there are all sorts of different measures, like closest point of polygons or average distance. There's all sorts of things.
Yeah.
Do you have a method for spatial data analogous to resampling in which you try different definitions of the neighborhood boundaries?
I guess you'd need a really good theoretical reason to define different neighbors, right? I don't think that kind of resampling approach would be effective here unless you have a reason to define your neighborhoods totally different. Like maybe you want to try the same measure using contiguous neighbors or distance band based neighbors, or have different weights that introduce like a decay. But I don't think just arbitrarily creating your neighbors is informative or helpful anyway, right? Because then we're kind of losing track of what is that spatial relationship.
Fair. And I guess you sort of did resample when, like, during your permutations of you're permuting which ones are actually neighbors or not.
Yeah, because we're trying to simulate complete randomness, right? By just arbitrarily choosing from a uniform distribution, right? So in that case, yes, absolutely. And if you want to try that out, there's a function called cond perm NB to conditionally permute that neighbors list.
And you did talk about, I think, Moran eyes, how you did it, like how to differently weight points based on their distance from you.
You can do that, yeah. So that if would follow the point pattern approach. So typically, if you're going to be doing points, the most common way of identifying neighbors is just through the k nearest neighbors based on distance. And then you can use their distances as weights, but also what you can do is use a kernel. So those kernels, their intention is to introduce more decay. So say you have 5-point neighbors, but they're all at different distances. So what you can do is use a kernel that rather than just kind of like using their pure distances, it introduces some sort of additional decay, or it inverts the distances to kind of add more influence to nearer points than more distant ones.
This is a comment, but GLMM fields is a niche package for Bayesian regression of multivariate T random fields. What do you feel like? It's not a question, so you don't have to answer, but someone wanted to throw that in there back when you're talking about some modeling.
Yeah, I'm just opening up the package so I have it to look at later.
Nice. And is there's someone responding to when we talk about modeling packages. So that's another way to modeling. Then is SFDEP on CRAN?
Yes.
Congratulations. I know that was a thing you're working on.
Yeah, there's a lot of undocumented things that you got to get right.
Oh yeah.
So even though I was passing all my local checks, it took some extra time to get there, but I wanted to get it on there before this happened. So nice. It is. Congrats. So you can, I probably missed that step. You can install it from CRAN using install out packages.
So I've been following you on Twitter of your journey of having to get this up there. And it seemed hard, as it always is. So congratulations on getting it up there.
Yeah. I didn't know you had to have R packages in single quotes in the description of your description, for example.
Yeah, and there's arbitrary rules that aren't necessarily told to you, but once you submit, they tell you you're wrong, then you can make it right.
Yeah, I mean, I just feel like it's nice, but it's just a lot of extra steps where if it was just in the check, I could get it there a little bit faster with fewer interruptions. Yeah.
Yep. This is a selfish question, but I know I have a lot of friends and a wife who does a lot of brain imaging, and the brain is a 3D map. Have you applied any of your stuff? Because you did mention altitude. Have you done 3D spatial stuff with SFDEP?
No, but I know Michael Sumner here is always talking about considering meshes. No, I haven't. I think part of that is just that my interest is largely around urban things. So like I mentioned, Airbnb, 911, crime, educational attainment, and all those are very flat. I think that is a very valid thing to explore. I just don't know how it would fit into these statistics that I'm familiar with, right? Like, how does elevation play? I guess you could have the distance from elevation play an important factor, right? Because you're calculating distance along as altitude, that does play, but that's a very minor change.
Yeah, I'd be interested because I remember my TA in grad school did spatial stuff. He had to think about, he actually did like a group lasso using parts of the brain. He had to build a network about what were connected and what wasn't. So over here, I think that was everything. Oh, and Michael Sumner coming in, talking about how you could apply spatial to non-geo stuff. Yep. So that is and again, the brain is just a map, right? It's not just a map. It's just one way to look at it. Lots of things. Oh, there's one more question. There's always a sneak in. Actually, this is a question. I've been using this a lot. I want to hear Josiah's take on the Uber's H3 for binning your data.
I was just thinking about this the other day. So I think it's so cool. There's a package on GitHub that I've been waiting for over a year to be on CRAN, but I don't think anyone's taken the steps. It's really, really, really nice. I just don't have the familiarity with C and make files to do it myself.
You're talking about the H3 package that's still sitting there in GitHub. It's like crazy Paeka is the username.
Yeah, yep, yeah.
So I wanted to use that one, but since it wasn't on CRAN, there's another one called H3 JSR.
Yeah, that uses the V8 as a way to,
And so I used that, and I've been using the not for binning, but for like finding things that are just near each other. So I'm doing a lot of distance between points. So I'm using the hexagons to find what are near each other. And then once I find what they're near each other, I can find what's sort of near those, and I can compute much smaller distance matrices. So I like it. So Jeff H, I really like using it, and it's fast. Like you ask for it, and it comes back like that with the H3 indicators. But Josiah?
Yeah, absolutely. And it's also really cool because so the company SafeGraph, which I mentioned earlier, they sell tons of point of interest data. And I think they're like incubating a company called PlaceKey. And PlaceKey is like, it creates this unique identifier for every POI, at least in the US. I know they're expanded to Canada, and all of those are based on the H3 grid that it falls in. So if you can have, like, they have an API where you can just send addresses that like they handle the formatting and so on and so forth, and it returns this place key so that you can kind of geolocate and join across data sets and not have to like perfect addresses and all the idiosyncrasies across databases. I think it's really cool, and it's based on H3 as well. And that's how I actually learned about H3, was through that. So the applications are wide, and it's super, super cool.
Yeah, it's been helpful for me. So, and Josiah's gonna get into it. I do love H3. Just even for like, I use H3 to go from a point to a hex to a different point, and it's been very, very helpful.
That's awesome.
Yeah. All right. So with that, just a few reminders to close things out. And if there's another question while I'm giving reminders, so be it. Remember, we have May is virtual. June will be both in person and virtual. We have the New York R conference coming up June 8th through 10th. Use code NYHackR30 for 30% discount on both the workshops and the conference itself. Check out you get tickets to the conference at rstats.ai. Check out nyhackr.org for the meetup site, including in this video and these slides will be posted to that site in a few days. So I guess if you're watching this, not right now, you're watching this recording, you're already at the site, but it is available. You have 13 years worth of slideshows, because today is the 13th anniversary of the meetup. Just a big thank you to Josiah for this wonderful talk. Everyone, let's give another golf clap to him. And then thank you everyone for being here. Thank you for Josiah for talking, and I'll see everyone next month. Stay tuned for the next announcement. Bye, everybody.
Awesome. Thanks, Jared.
Thank you.